I'm going to work some more problems from the final study guide. I'm going to start with number 19 from your final review study guide for your college algebra final exam. Starting at number 19, the material comes from section 1.7 in your book, and we're doing quadratic and rational inequalities. Now when you work these, you'll need to find your boundary lines, but then you'll have to check the regions to see what works, so there's a follow-up piece to these. So you start working it as if it were a regular quadratic, but notice it is an inequality, meaning a less than or greater than problem. So you bring your quadratic over to one side, get it in standard form, isolate it as you do any equation, then factor it or use your formula, set each factor equal to 0. So you get two solutions, -4 and -3. But again, we're not finished. Those are just the boundary lines that cuts the number line at those two places, at -4 and -3. It divides the number line into 1, 2, 3 regions. We don't know whether it's these two regions, outside regions, that solves it, or the inside region. So we have to use a test point. So you take a test point, you use test points to determine which regions are the solutions. So I always like to find 0. It's an easy number to work with. So look at your number line and say which region is 0 in. In this particular problem, 0 is the far right side. So I'm going to see if that region works. If so, it looks like it'll be these two parts, and the middle will be not used. If not, it's the middle. It's either the outsides or the middle. All right, so I'm testing 0 back in the original problem. Is 0 squared plus 7 times 0, that would just be a big 0, 0 squared, 7 times 0, less than or equal to -12. So the question is 0, that's 0 when simplified, less than or equal to -12? And actually not, 0 is bigger than a negative, so that is not true. So that is not a region that we shade. And it's usually every other one. We could test something between here, like -3.5, and double check that, but it looks like everything in this region works. And then if we test something like -5 over here, in that, it should not work. So nothing in this region works, nothing in this region works according to our test point, so it's the middle region that works. If there is a line under this, this means we include the endpoints, the boundaries, so that means a bracket around those two endpoints. So the final solution in interval notation is every number between -4 and -3, including the endpoints, should solve that inequality, should be the solution set. All right, number 20. The next situation we're going to see is a rational inequality, also from section 1.7. The first step on a rational inequality is have it set equal to 0, just like the quadratic. So this one's already equal to 0. So then we proceed to the next step, which is setting the numerator equal to 0 and the denominator equal to 0. And that will give me these boundary points, like we just saw in the last problem, boundary regions. So solving this, I get 7, a boundary line at 7, and then at -8. So I make my number line, and I find -8 and +7 splits this into 3 regions. And then I'm looking for which regions work. And so I find my test point, which I usually like to use 0. Between -8 and 7, 0's in the middle. I plug it in the original inequality to see if it works. 0 minus 7 over 0 plus 8, is that less than or equal to 0? So that's -7/8 when simplified. -7/8, because it's negative, is less than or equal to 0. That is true. So that region that contains 0 is part of the solution. Everything in there should also work. You could test another point if you want to see that it's so. Anything between -8 and 7 should give you the same result, that it solves that. And then, to save time though, you could, I'm not going to do it, but you could check something out here like 8, 9, 10, a million, whatever number in that region when plugged in should not work, not part of the solution. And then checking over here like -9, -10, again plugged in should not work. The only region that solves it is between -8 and 7. All right, now this is a really important, tricky little detail though, because on the last problem, I just got through telling you if there's a line under it, you should use a bracket because you include the endpoints. Well, We should try to include the endpoints, but we cannot include an endpoint that makes the denominator equal 0. You cannot include negative 8. You cannot include that in the solution set because it would make it undefined. Anything that makes the denominator 0 makes it undefined, and it can't be part of the solution. So we exclude negative 8 with a parenthesis, but include the other boundary points as possible because that's what makes the numerator equal 0, and that's okay. So the solution is parenthesis, negative 8, and a bracket around the 7. So be careful about that little detail. All right, we're going to see a similar situation on number 21. It'll be the same problem pretty much, except the first step we're going to have to get it equal to 0 first. So a little step up in difficulty, but pretty much the same problem. So step 1 on this one, we need to bring the 15 across the line, make it equal to 0 before proceeding. Now I've got minus 15. And so we want to consolidate these two fractions into one fraction before we can proceed with the steps like on the last one. So think of negative 15 as being over 1. Get a like denominator, which will be this denominator, under each one so you can combine these two fractions. So this fraction stays as is, but here we say 1 has been times by this new denominator, so we have to times the top also by that value to keep the balance. So now these two fractions have like denominators, so now we can consolidate or combine those two fractions. So we got 5x, and then I distribute the negative 15, don't forget to pick up the negative sign to distribute that, which will make that a plus 15, oh, wait a minute, it's, yeah, plus 45, I knew something didn't look right. 15 times 3, 45x, and negative 15 times 14, I need my calculator again. 15 times 14 is 210. And that's all over that common denominator. Now we can combine 5x and 45x to be 50x. And then finally, I mean that was a lot of extra little bit, but really all we were doing there was combining algebraic fractions. We get it into one fraction, and 0, then we can do the same thing we just did on the last one. So you'll need to set numerator equal to 0 and denominator equal to 0. That's where your boundaries are. Keep in mind what makes the denominator equal 0 cannot be included in the solution. So this boundary will have a parenthesis, not a bracket. All right, I'm going to erase this to make room now to proceed. So we set the numerator equal to 0 and the denominator equal to 0. So solving this first one, bring the 210 over, divide by 50. That doesn't come out perfect, so we just want to leave it as a fraction, reduce that fraction to 21/5. That's one of our boundaries. Do the same thing on the second one, solve this equation, and we get positive 14/3, the other boundary. Those two answers are pretty close. You might have to really think about this from your arithmetic. Which one's smaller, so I know where to put it on the number line. What you may need to do is divide that on your calculator and see it's like 4.2, and this one's 4.6. So this one's actually the smaller fraction, so it goes on this side. Why I made that negative. It's 21/5, and then this is the larger fraction, 14/3. Again, remember when we do this procedure, these are only boundary lines, cutting the number line into regions. 1, 2, 3 regions in this case. So it's either the middle region or the two outer regions, and you have to check a test point to see what works. Always find my 0. 0 would be the far left in this example. So I'm going to plug 0 back into the original equation, way back here to the original equation. I'm plugging in 0 for my x's to see if that makes it true, if it's part of the solution. You know, if it's true, that means it solves it. So 0 over anything is 0. Is 0 greater than or equal to 15? It is not, so that does not work. So we're assuming this one does. To be absolutely sure and to be more thorough, you should take a point between those two fractions, which will take a little bit of thought. and plug it in and see that it solves. Anything between 21/5 and 14/3 should work. And then again, you can check over here, like maybe 5, 6, 7, whatever number past 14/3 you like to plug in, you should verify that does not work. This is the region that works. Then remember the little tiny detail, you've got to know that whatever makes the denominator equal 0, which was the 14/3, has to be excluded from the solution. Parentheses mean we don't actually include that, just real close to it, excluding that endpoint. But because there's a line under it, we include the other endpoint, the one that made the numerator equal 0. So the final answer in interval notation is from 21/5 to 14/3, half parenthesis, half bracket. Do you have time to do one more? Okay. All right. The next concepts, starting at number 22, start with section 1.8, absolute value. All right, so on this first example, we have an absolute value equal to an absolute value. These are our absolute value bars. So there's two possibilities, and that's kind of the theme of this whole section, is there's two possibilities for most of these, a positive and a negative. But the two possibilities here is what x would make those two amounts equivalent? What would make this quantity equivalent to this quantity? What x value, when we solve that, makes these two sides the same value, the same number? Or the other solution would be what makes them opposite sign. If one of these were a negative and the other one positive, like say this was a -7, this is a +7, their absolute values are still 7. So that would work. They could be opposite in sign and still be equivalent because of the absolute value signs. So which side do you make negative? It does not matter. It comes out the same result, believe it or not. So whichever side you feel like, I usually just do the second side. So I would take a negative times this side. And then that's my two problems to solve. So here, solving for x, I'll bring my x's to the same side, constants to the other side, dividing, x is 1. Check it out, and it does work. If you plug in 1 for these x's, -6 plus 3 is -3. 1 minus 4 times 1 is also -3. See, that's what we ask it to do, what makes these two equivalent. If I plug in x is 1, they're both -3s, therefore their absolute values would both be 3, works. All right, the other possibility is that they're opposite signs, not necessarily by 3s, but just some x value, we're going to find it here. So we would distribute the negative sign, bring our x's together, bring our constants to the other side, and solving that, I get if x is -5, these two are opposite. Let's just see that this is so. So plugging in a -5 for these x's. -6, that would be -15. That's -21. I'm hoping this side's +21. -4 times -5 is 20 plus the 1. There it is. So if this side's -21, that side's +21. They're opposite in signs, but absolute values would be equivalent. So these are our two solutions, 1 and -5. The solution set.